A telescope a million miles from Earth pointed its mirror at the darkest, oldest patch of sky anyone had ever tried to read. Scientists expected faint smudges. What came back looked like finished cities standing where empty fields were supposed to be. 6 of those objects would earn a nickname no astronomer wanted to use seriously, and yet they kept using it anyway: universe breakers. Here is the question this investigation will not let go of. Did the James Webb Space Telescope catch the early universe doing something genuinely impossible, or did it catch scientists making a measurement mistake at the edge of what their instruments could resolve? We are not going to pretend the answer is settled, because it is not. What we can do is walk through the evidence the way the researchers themselves had to walk through it, one confirmation and one doubt at a time. Start with what the telescope is actually built to do, because the rest of this story does not make sense without it. The James Webb Space Telescope reads infrared light, the part of the spectrum that sits just past what human eyes can register as color, the same kind of radiation your skin gives off as heat. Light behaves like a sound wave stretching as its source pulls away from you, the pitch dropping the farther and faster it travels. Astronomers call that stretching redshift, and because the universe has been expanding since its birth, almost everything distant is rushing away from us. The farther a galaxy sits, the more its light has been stretched, and the more it slides out of visible color and into the infrared band that only an instrument like Webb can read cleanly. That stretching does something else, something that turns the telescope into an instrument for reading time rather than just distance. Light needs time to cross space. A galaxy 9 billion light-years away is not showing scientists what it looks like today. It is showing them a photograph taken 9 billion years ago, light that has been in flight ever since, only now reaching a mirror built to catch it. Push that logic far enough and you reach a limit, a boundary scientists call the observable universe, the farthest distance light has had time to travel since the cosmos began. Beyond it is not empty space. It is simply light that has not arrived yet. The galaxies sitting at that limit are not just far away, they are old. The farther out you look, the closer you get to the very beginning of cosmic time, an era researchers call cosmic dawn, when the first stars and the first loose gatherings of stars were just beginning to switch on. For decades before Webb ever launched, cosmologists had built a careful, well-tested model of what cosmic dawn should look like, and it is worth being precise about what that model actually predicted, because the prediction is the baseline every later measurement gets checked against. The model starts right after the Big Bang, with a universe of almost perfectly smooth gas, nothing but hydrogen and a smaller share of helium, the 2 simplest elements there are. Gravity pulled on the slightly denser pockets of that gas first, slowly, patiently, over many millions of years, until enough material piled up in one place to ignite. The first stars switched on. Small groups of those stars gathered into the first galaxies, and the model said those galaxies should be modest, faint, loosely built, made almost entirely of light gas, because the heavier elements, carbon, oxygen, the building blocks of planets and people, had not been cooked yet. That cooking only happens inside stars, and it only gets released into space when a star dies, so the early universe was expected to be chemically plain by necessity. There simply had not been enough generations of stars living and dying to enrich it. Just as important as what the model predicted is how it was built. This was not a guess dressed up in scientific language. It rested on decades of observation of the nearby universe, on detailed computer simulations of how gas collapses and stars ignite, and on the leftover glow of the Big Bang itself, a faint background radiation that maps out how matter was distributed when the cosmos was only a few 100,000 years old. Feed that map into the physics we trust and run it forward, and you get a specific, falsifiable prediction. Cosmic dawn should be a slow sunrise, small galaxies merging gradually over hundreds of millions, even billions of years into the grand spiral galaxies we see around us today. The model worked beautifully for everything closer to home. It explained galaxy clusters, it explained the rate at which stars form in galaxies we can study in detail, it explained the chemical makeup of the cosmos as far back as anyone had been able to look. Confidence in it was not blind, it was earned. So when the James Webb Space Telescope launched and scientists started planning where to point it first, nobody was expecting to overturn that model. They were expecting to confirm it in finer detail than ever before. to watch the slow sunrise actually happen, frame by frame, for the first time in human history. One of the earliest deep observing campaigns built around that goal was called the Cosmic Evolution Early Release Science Program, known by its acronym CEERS, designed to point Webb's main camera at a patch of sky already studied by the Hubble Space Telescope and stare at it for hours, letting faint ancient light slowly accumulate until galaxies too dim for any previous instrument finally became visible. What came back from the CEERS data was a handful of objects so red, so faint, and so strange in their colors that Lebes's team almost set them aside as noise, the kind of artifact that shows up in new instruments before anyone has learned its quirks. They did not set them aside. Instead, they ran the numbers, and the numbers kept producing the same uncomfortable answer no matter how many times the team checked their work. 6 objects in particular stood out. Based on their colors, their light placed them at a redshift between roughly 7 and 9, which translated into an age of somewhere between 500 and 700 million years after the Big Bang. On the timeline the standing model had laid out, that placed them deep inside cosmic dawn, in the era when galaxies were supposed to be small, faint, and just beginning to take shape. These 6 were not small. When the team estimated how much stellar material each one contained, the figures came back in a range that should have been impossible at that age. One of them appeared to hold roughly as many stars as the present-day Milky Way, a galaxy that took more than 13 billion years to build its full mass. This object appeared to have assembled a comparable amount of stellar material in under a tenth of that time, and it had done so inside a volume of space roughly 30 times more compact than our own galaxy, packing that much light and mass into a tight, dense knot rather than spreading it out across a wide, settled disk. Lebes was blunt about the team's own reaction. In comments given shortly after the result became public, he described the moment plainly, saying that he and his colleagues did not initially believe what they were looking at, that there could not be galaxies this mature so early in cosmic history, and that the result needed to be checked and rechecked before anyone trusted it. He used a word that stuck. The team was, in his telling, mind blown, almost unwilling to accept their own data at face value. That kind of reaction from a working scientist is itself a piece of evidence worth sitting with for a moment. Researchers spend careers learning to distrust surprising results, because surprising results are usually wrong. The fact that a measurement survived that instinct and still looked wrong relative to the model is part of what makes this case different from an ordinary anomaly. Leja, working alongside Lebes at Pennsylvania State University, gave the 6 objects the name that would follow them through every headline that followed. He called them universe breakers, and in a statement released alongside the team's published findings, he put the stakes in plain language. The discovery that massive galaxy formation appeared to have started so early in cosmic history upended what a great many researchers in the field had treated as settled science. He added that the team had been using the nickname informally among themselves, and that the objects had, in his words, been living up to it. The team's full analysis appeared in the journal Nature in February of 2023, a paper formally titled, "A Population of Red Candidate Massive Galaxies Around 600 Million Years After the Big Bang." The choice of the word candidate in that title is not incidental, and it matters for how seriously to weigh everything that came before it. We will return to exactly why that word was doing careful, deliberate work in a moment. First, it is worth understanding how the team actually arrived at these numbers, because the method carries real limitations that the researchers themselves flagged from the very beginning. Webb's camera, known as NIRCam, captures images of the sky through a set of different filters, each one sensitive to a particular slice of the infrared spectrum. By comparing how bright an object appears across several of these filters, astronomers can estimate roughly how far its light has been stretched, and from that, roughly how old and how distant it is. This approach is called photometric redshift estimation, and it is fast, useful, and capable of scanning thousands of objects across a single image in a way that more precise methods cannot match. It is also, by the admission of nearly everyone who uses it, an estimate rather than a verdict. A handful of brightness measurements across a few filters can be fooled. Dust can redden a nearby galaxy's light in a way that mimics the redness of a genuinely distant one. A burst of glowing gas around young stars can spike the brightness in one filter and throw off the whole calculation. The 6 universe breakers were identified through exactly this method, which means their extreme distances and their extreme masses were both built on an estimate rather than a confirmed measurement. The team understood this limitation better than anyone reading about it later would. Even in the earliest public comments about the discovery, Labbé acknowledged that some of the 6 objects would likely turn out to be smaller or less extreme once better data arrived, while adding that he expected at least some of them to hold up as genuine. He framed it as a wager rather than a certainty, saying the coming year would tell researchers which way it broke. That is a strikingly different posture than the one suggested by the headlines that followed, many of which dropped the word candidate entirely and reported the 6 galaxies as a confirmed, settled violation of cosmology. The actual claim being made by the people who did the work was narrower and more careful than that. There was a second complication buried inside the brightness measurements themselves, one that Leja raised publicly almost as soon as the result was announced. A galaxy can shine because it is packed with stars. It can also shine because something else entirely is generating the light, something that has nothing to do with stellar mass at all. Leah noted explicitly that it was possible some fraction of these 6 objects were not ordinary star-filled galaxies at the dawn of time, but something stranger. Compact regions surrounding feeding black holes, dense enough and bright enough to mimic the photometric signature of a fully formed galaxy without containing anything close to the stellar mass the brightness alone would suggest. That possibility did not make the puzzle disappear. It split it into 2 separate puzzles, each one strange in its own way, and we will need to follow that thread carefully in the chapters ahead. Spectroscopy spreads a galaxy's light into a full, continuous spectrum rather than sampling it through a handful of broad color filters. And inside that spread of light, individual elements leave exact, unmistakable marks. Hydrogen absorbs and emits light at very specific wavelengths. So does oxygen and carbon and every other element on the periodic table, each one producing a pattern as distinctive as a signature. Because researchers know exactly where those signature lines sit when an element is standing still, and because the expansion of the universe shifts every one of those lines toward the red end of the spectrum by a precise, predictable amount, reading a spectrum gives a redshift measurement with a level of certainty that photometry simply cannot match. It is the difference between estimating a building's height from its shadow and walking up with a tape measure. The cost of that certainty is time. Spreading a faint, distant object's light into a usable spectrum requires gathering far more photons than a quick image does, which means pointing the telescope at a single target for many hours, sometimes tens of hours, rather than capturing it in a single exposure alongside thousands of other objects. Webb's spectrograph, known as NIR-SPEC, can only be aimed at a limited number of targets in any observing run, which meant researchers had to choose carefully which of the candidate objects from the photometric surveys were worth that investment. The 6 universe breakers, given their stakes, moved to the front of that line almost immediately. The results, once they came in, were mixed in exactly the way a careful reader of the original paper might have expected. Some of the 6 did not survive contact with spectroscopy in their original form. When researchers read their light in full detail, a portion of the extreme brightness in certain objects turned out to come from strong emission lines, the kind produced by hot, glowing gas surrounding young stars, landing inside one of the broad photometric filters and inflating the apparent brightness beyond what the actual stellar population could account for. Once that contribution was subtracted out, the implied stellar mass for those particular objects dropped, in some cases substantially. This was precisely the outcome the more cautious voices in the field had predicted from the start, and it is worth giving that prediction its due. The photometric method had overstated at least some of the original claims. What spectroscopy did not do was make the broader problem disappear. Across the growing catalog of objects identified in CEERS and in subsequent surveys, a clear pattern held even after the most extreme individual claims were trimmed back. Galaxy after galaxy, once its distance was pinned down with a confirmed spectroscopic redshift rather than a photometric estimate, still sat earlier in cosmic history and still appeared brighter and more massive than the standing model allowed for its age. The extremes softened. The underlying pattern did not. Researchers who had hoped a wave of corrections would quietly dissolve the entire controversy found themselves instead looking at a smaller, more tightly confirmed version of the same puzzle, one now resting on the most reliable measurement technique available, rather than on a quick estimate that anyone could reasonably doubt. It was in the middle of this confirmation process that an entirely new category of object began showing up across multiple independent surveys, and it would end up reframing the whole argument. Researchers including Dale Kochevsky, Yuichi Harikane, and Jorat Mathie, working with separate teams and separate datasets, each began noticing a population of small, intensely red, almost perfectly compact points of light scattered through the early universe in far greater numbers than anyone had anticipated. Mathie's team gave the population the name that stuck across the field: little red dots. The little red dots presented a puzzle of their own, distinct from the mass problem raised by the original 6 galaxies, though closely related to it. Their light carried a strange, almost contradictory signature. Part of their spectrum resembled the broad, fast-moving gas signals associated with materials spiraling into a feeding black hole, the kind of signal that, on its own, points clearly toward an active galactic nucleus rather than a population of ordinary stars. But another part of their light looked surprisingly settled, more like the calm glow of an established stellar population than the violent activity expected around a young, hungry black hole. Kochevsky's team, working through Webb's extragalactic survey fields, identified a sample of these broad-line objects at redshifts beyond 4 and described them as faint but unmistakably present in numbers far higher than standard models of black hole growth predicted for that era. Harikane's independent survey using NIRSpec reached a similar conclusion from a separate dataset, identifying roughly 10 faint active nuclei in the same early epoch, each with estimated black hole masses in the range of 1 million to 100 million times the mass of our Sun, sitting inside galaxies that themselves looked too small and too young to host them comfortably. This mattered enormously for the original mass controversy because it offered a second possible explanation for at least some of the extreme brightness driving the universe breaker claims. If a meaningful share of an early galaxy's light came not from a vast population of stars, but from a single feeding black hole at its center, then the implied stellar mass for that object could shrink considerably, easing the pressure on the timeline for how fast stars could form. Leicia's original caution, raised the moment the 6 galaxies were announced, had effectively predicted this outcome before the little red dot population was even formally identified. But trading one explanation for another does not make a puzzle vanish. It relocates it. Black holes growing to 1 million or more solar masses within the first several hundred million years of cosmic history is, by the standard model of black hole formation, close to its own kind of impossible. Conventional models hold that black holes grow gradually, starting from much smaller seeds and adding mass slowly over time, constrained by a rough physical speed limit. Feed a black hole too quickly, and the light generated by infalling, superheated gas pushes the remaining material away before it can fall in, choking off the very growth that would otherwise occur. Reaching the masses implied by the little red dots within the available time would require either an unusually massive starting seed or a sustained rate of feeding well above what that speed limit is generally thought to allow. Adding to the uncertainty, the question of whether the little red dots are even reliably powered by black holes at all remains genuinely contested within the field. A study led by Mitsuru Kokubo and Yuichi Harikane examined the variability of these objects across multiple observing epochs, reasoning that a true feeding black hole should flicker and change in brightness over time in ways that a settled population of stars would not. They found no clear evidence of that variability and no strong detection in X-ray observations, both of which are commonly associated with active black holes elsewhere in the universe. Their conclusion challenged the active nucleus interpretation directly, leaving open the possibility that at least some little red dots are something else, a kind of dense, compact stellar structure not yet fully understood, rather than a disguised black hole at all. Researchers have 2 independent roads to that number, and for most of the history of modern cosmology, both roads were expected to converge once the measurements got precise enough. The first road stays local. Astronomers identify a class of stars whose brightness pulses in a steady, predictable rhythm, the speed of that pulse revealing how intrinsically bright the star truly is. Compare that true brightness to how dim the star appears from Earth, and you get a reliable distance. String enough of these distance measurements together across a chain of galaxies, known as the cosmic distance ladder, and you arrive at a directly measured value for how quickly space is stretching nearby. The second road starts at the opposite end of cosmic history entirely. It reads the faint background radiation left over from the universe's infancy, a detailed map of how matter was distributed when the cosmos was only a few 100,000 years old, and feeds that map into the same trusted physics used to predict cosmic dawn, running the model forward to calculate what the expansion rate should be today. For decades, refining both methods was expected to bring their answers closer together. Instead, as each side got more precise, the gap between them held steady, and then, by some measurements, widened slightly. The local method consistently returns a value in the low 70s, in the units astronomers use for this number. The early universe prediction consistently lands a few units lower, closer to the high 60s. Researchers gave this stubborn disagreement a name, the Hubble tension, after Edwin Hubble, the astronomer whose original observations first revealed that the universe was expanding at all. A gap of only a handful of units might sound trivial, but the uncertainty on each side of that gap has shrunk so far that the disagreement now sits well outside what either method's margin of error can explain away. Two of the most heavily scrutinized measurements in the history of physics, each backed by decades of refinement and thousands of contributing researchers, are pointing at two different answers to the same basic question, and neither side is wrong by any obvious or correctable amount. That combination is what elevated the Hubble tension from an interesting footnote into one of the most closely watched open problems in cosmology. There are only two broad ways out of a disagreement like that. Either a hidden, uncorrected error sits somewhere in one of the measurements, or both measurements are accurate and something genuinely new is shaping the expansion of the cosmos between the early universe and now, a piece of physics the standard model has not yet accounted for. For years, the more hopeful possibility, at least for researchers who preferred not to rewrite the textbooks, was the first one, and the leading suspect for where that hidden error might be hiding sat squarely inside the local measurement, in the very stars used as the first rung of the distance ladder. Those pulsing stars, known as Cepheid variables, sit inside distant galaxies crowded with countless other stars nearby. Through the resolution available before Webb, a Cepheid's light could blur together with its neighbors, and a blurred blob of overlapping starlight can appear brighter than any single star within it really is. A star that looks artificially bright gets judged artificially close, and if that kind of crowding error had been happening systematically across the Cepheid sample, it could have inflated the local expansion measurement just enough to manufacture the entire tension out of nothing. This was, for a meaningful stretch of the 2010s and early 2020s, the field's best hope for a quiet, mundane resolution. Wendy Friedman, an astronomer who has spent much of her career on precisely this measurement, raised the crowding concern directly, proposing that a closer look with sharper instruments might reveal the local number to be lower than previously reported once the blur was properly accounted for. Webb was built with exactly the resolution needed to test that hope directly, and Adam Rees, an astronomer at Johns Hopkins University who leads the SH0ES research collaboration, set out to do precisely that. Rees and his team used Webb's superior resolving power to reobserve Cepheid variables in several galaxies already measured by the Hubble Space Telescope, including a deliberately challenging target in a galaxy called NGC 7250, selected specifically because it had been proposed as a case where crowding might be distorting the result the most. Webb's sharper view let the team separate individual Cepheids from their crowded neighbors far more cleanly than any previous instrument could manage. The old measurements held. Published in the Astrophysical Journal letters in early 2024, Rees and his co-authors reported that the Webb data matched the original Hubble measurements closely, with no significant difference attributable to crowding, ruling out unrecognized crowding as an explanation for the Hubble tension at a confidence level the paper's own title states directly: 8 standard deviations, a level of statistical certainty far beyond what is normally required to consider a result settled. Rees summarized the result plainly, stating that the team had now spanned the full range of galaxies originally measured by Hubble, and that a measurement error could be ruled out as the source of the tension with very high confidence. The team extended this work further still, eventually covering 8 separate supernova-hosting galaxies and roughly 1,000 individual Cepheid variables, reaching as far as a galaxy called NGC 5468, located 130 million light-years away, which represented the outer edge of what Hubble itself had originally measured. This should have closed the door on the mundane explanation. It did not close it entirely, because Friedman's own follow-up work, also using Webb, complicated the picture rather than simplifying it. Rather than relying on Cepheids at all, Friedman's team turned to a different class of distance markers, including a method called the tip of the red giant branch, chosen specifically because it is far less vulnerable to the crowding problem than Cepheids are in the first place. Analyzing 11 galaxies with this alternative approach, Friedman's team reported a measured expansion rate in a range between roughly 68 and 72 units, a result she described, in a public statement accompanying the paper, as not lending strong support to the idea that fundamental physics is missing from our understanding of the early universe. Her stated conclusion went further, suggesting the standard cosmological model might be holding up better than the tension implied. So by the middle of the 2020s, two separate teams, both using the same telescope, both publishing in respected journals, had reached two different conclusions about the very same open question. Rees's Cepheid work confirmed the original high local value and explicitly ruled out the crowding explanation. Friedman's alternative method suggested a lower, more compatible value using different tracers entirely. Researchers in the field have not resolved which approach is closer to the truth, and that disagreement is not a sign of sloppy work on either side. It is what an unsettled measurement looks like while it is still being actively contested by careful people using the same instrument and arriving in different places. The mundane explanation for the Hubble tension has not been confirmed. Neither has it been ruled out entirely. And that unresolved status sits right alongside the unresolved status of the universe breakers, two separate cracks in the same model surfaced by the same telescope in the very same handful of years.